Hello everyone, I'm Pronnoy Goswami. I'm excited to be presenting at DevOps 2026 organized by Conf42. I'm thankful for the opportunity and today I will be speaking about from signal to insight how I've built a queryable observability dashboard and a tool chain using MCP, which is the Model Context Protocol. So let's get into it. About me. So I'm currently a software engineer at Workday, and previously I've had stints at McKinsey, Microsoft, PayPal. I'm experienced with distributed systems, AI, and cloud infrastructure, and my work focuses primarily on AI ML infrastructure and observability. I often write about my findings and my learnings in my blog on LinkedIn called Distributed by Pronnoy, and these are my socials. So I'm excited to be sharing this presentation with you. So now let's get into the weed of things. Why should you actually care, and what's in it for you guys who's attending the conference? So let's imagine a scenario like we have all been there as on-call engineers that we get a 2 a.m. page, and whenever we get on that, we start looking into the data avalanche. Like tens of terabytes of logs daily are being ingested in a platform or services, millions of metrics and data points, millions of distributed traces, and thousands of correlation IDs per minute. And what we struggle with most is manual correlation across systems, tribal knowledge dependency, alert fatigue, and delayed root cause analysis. So, from what we have seen so far in our careers, is that we don't have a data shortage problem because data today is not the scarce commodity, but we have a data context or meaning problem. And that's what I'm going to solve with my proposed new architecture, from converting observability from a reactive standpoint to a more proactive and measured approach. So let's look at why modern observability fails. So we all know that observability, there are three key pillars in observability, which is metrics, which tells us essentially what is happening, logs tell us why it happened, and traces where it happened. And the core problem is that without the consistent thread of context, debugging, and manual correlation, it becomes really hard. And this has been actually backed by data. So 50% of the organizations report siloed telemetry and only 33% achieved unified views across metrics, logs, and traces, according to the 2023 Observability Forecast report by New Relic, which has been cited. Let's look at the paradigm shift that we are observing and that we have leaned into to solve the problem. So traditional observability correlation at incident time. So whenever we get an incident, we correlate and draw the path of the whole incident, how it happened, why it happened, and understand the context. The minimum time to detect, resolve becomes slower. However, in the new approach, the minimum time to detect, resolve becomes faster. There is higher alert fatigue on the on-call engineers or an SRE and reduced developer productivity. However, on contrast, by this approach, we feel that there would be lower alert fatigue, increased developer productivity, and so on. So let's look at model context protocol, which lies at the heart of this whole data pipeline for the AI enhanced telemetry. So MCP is I think we all have might have worked with it or heard about it, but MCP is an open standard that allows developers to create a secure two-way connection between data sources and AI tools. So if we look at the image, here MCP, there is an MCP server that connects with different large language models like Anthropic's Claude, Opus, or OpenAI's OSS, and then there are different tools or services that get integrated. There are three key components here. So one is the contextual ETL for AI. So for any AI model, I think the most important part is like how do we provide them the right context and data. So it standardizes the context extraction for multiple data resources, basically defines a schema of what our data should look like across different services and resources, a structured query interface so that the AI models can interpret and get transparent access to these enriched data layers. The semantic data enrichment embeds meaningful context directly into the telemetry signal that we have received, for whether it be metrics, logs, or traces. So let's deep dive into the proposed architecture. This essentially can be called as a three-layer architecture. Here I have shown a payments processing microservice. It could be any microservice or also a monolith, but essentially it's here for more easiness of understanding. So we have an open telemetry exporter that emits raw metrics, logs, and traces. Then it goes into the service that does the OTel instrumentation and the context enrichment, which is the second box. And then the enriched telemetry is stored into, say, a telemetry storage like InfluxDB or Prometheus or something. Then there is an MCP server and an MCP query layer. The MCP server acts as an interface between the InfluxDB and the actual AI analysis engine, which is essentially the large language models fine tuned for specific observability. And then there are dashboards on top of that based on, again, APIs. I think today Grafana, we'll see for in the coming slides that Grafana and other have good integration with any of the large language models and the API interface layers. So the goal here and the key insight here is to shift observability from a reactive problem solving to proactive insights. Let's do an implementation deep dive without further ado. So the layer one, as we spoke about, is context enrichment. So I have here shown a code example where, again, this has been simplified and obfuscated for understanding. So for example, at step one, we generate the correlation IDs for context propagation. So here we look at the process checkout for a payment gateway like PayPal or Stripe, and then we generate here the order ID and the request ID, and then we initialize a context dictionary to enrich the spans. Another interesting thing here is that I am going to give you a walkthrough on how traces for distributed tracing are being enriched and how we have used this to reduce MTTR and basically adopt this and lean into this AI enriched data pipeline for observability. So the key idea here is that every telemetry signals contains the same core contextual data, which we can see here, and it can vary from case by case. So user ID, order ID, request ID, cart item count, payment method, service name, and the service version. So tomorrow, if something breaks or we see some high latency in the fulfillment service, like after the payment is done, there is a fulfillment service. Then there is a warehouse service that actually dispatches. So we know where actually the delay is happening or where the incident has happened. Now let's see a very simple example of context enrichment. So this is a very simple debugging scenario, and I've done a comparative analysis on how we see error messages without trace context and with trace context. So without trace context, we see something like payment failed, and we get some error, and then it fires an alert, and then the on-call engineer or the subject matter experts goes into and starts looking into logs for that event, and it takes a lot of time. It requires background knowledge. However, in the enriched case, we see that okay, there is an error at the same time, but we see that the request ID is there, order ID is there, user ID, service. So even in the first layer as different dimensions, we see that these traces have been enriched. So what it does immediately is that instant correlation via the request ID. We can backtrack this request ID and figure out where we went wrong. Service identification, the user assessment, and automated trace assembly, essentially. So we can see here how context enrichment helps with debugging scenarios with a very simple example, and this is very simple, and you can adopt it and make it more versatile for different use cases. Layer 2 is the MCP server, which is the structured query interface, which acts like an interface between the, as I said in the diagram, the InfluxDB or the telemetry storage database and the AI models. So here we do three things essentially, and step by step we index the telemetry spans based for efficient lookups via context field. We do filtering based on precise data segregation, so that like we apply different time-based filters. There could be different other filters based on different dimensions. Like for example, we know that during Black Friday, there are some deals that are happening on Amazon.com, So we might know that, okay, these are Black Friday lightning deals and we want to track if something goes wrong, how do we solve it? So there is filtering, and then at the last step there is aggregation. So this is very simple. The results for log and results. If log context and request ID is equal to the given request ID, we do a bunch of things and then we apply the time-based filter. Then this is the heart of the whole architecture. Here is the AI driven analysis engine. So it defines the analysis time window in step one. Basically, when we want to analyze, and this is exposed via an API on the Grafana dashboard or wherever you are viewing your telemetry. Like it could be for traces, it could be Zipkin or Jaeger. But again, this is just the internal heart of what the API does. So we define an analysis window which the user provides. We extract the relevant telemetry based on the context, current context. So we extract here metric names by values, we extract here traces and whatnot and logs as well. And then we calculate statistical properties to capture anomalies and AI recommendations, which is this part, which is essentially we are using z-score and checking the standard deviation to calculate and see if there is any anomaly in the current traces and the telemetry that we are seeing. So here context enables automatic cross signal analysis without manual intervention. So from the user perspective, it would just be that you enter the timestamp just like you do for looking into traces or logs, and basically the whole model and this whole infrastructure that is there, pipeline is there, would give you insights that okay, this is what has happened in the past 7 days. Right now we are seeing it as an anomaly or not, and what or whether it's right and everything looks good essentially from latency wise or error wise. So what is the impact that we have observed? So a real world impact from we've seen like the time that has been reduced from hours to minutes. So before adopting this and leaning into this pipeline, we saw that approximately 45 minutes times was spent in average incident resolution. We had to do manual log correlation, multiple context switches between tools, tribal knowledge required for developers, and a lot of high cognitive load. However, after this, we've seen approximately average our MTTR being reduced to 8 minutes. And it's been reduced because of automatic correlation. A single pane of glass unified view in observability. There is a silver bullet term called single pane of glass view or unified observability, and this allows us to do unified observability. We also get context driven insights and AI suggested and enhanced RCA. So you just get a boilerplate RCA and you can work on top of that based on the AI model's understanding of your context and how well you have propagated your context and given basically populated the enrichment dictionary. So we have seen 82% reduction in the MTTR, 65% reduction in alert fatigue, and 3.2x faster detection. Again, this has been right now in more of a beta phase within for the implementation, but again, we see massive potential here for adopting it. And recently, a lot of companies like open source companies like Elasticsearch have been using Elastic Stream that allows the same thing to happen. Like for logs, they can do context propagation and context enrichment in the elk layer, but it is again vendor specific. However, by this way, which is open source, you can be vendor agnostic and do a lot of enrichment and AI driven analysis on your end, and of course, use Elasticsearch for specific problem solving, because again that's also paper API pay as you go. So the cost also adds up, given observability is anyways a very costly business. So I think the question that was raised was, this seems like a lot of overhead. I think that would come to your mind as well, but it came to our mind as well when we were doing the decision making. Is the complexity worth the effort that we are spending? So let's compare two scenarios. What are the hidden costs that you are already paying? So usually we, like whenever we do capacity planning, we do put like around 20% of an engineer's time on call workload or like engineering efficiencies. So which is around 15 to 20 hours per week. 60 to 70% of alerts are unactionable or get auto resolved. Context switching. So there is a massive amount of study done here that 23 minutes, it takes 23 minutes to refocus after an interruption, whether it be just be chatting with a colleague or something else for you to get in the zone. And we all have been hurt by this multiple times. I have been, over my span of career of 10 years, I've been hurt by it multiple times. And then tribal knowledge, like critical dependencies on certain individuals, and you become the bottleneck in the whole process. However, if we invest in this, this is again a one-time setup, and it could just be iterative increments. You don't have to boil the ocean at once. You can just implement one service and focus on that which is your most critical service, and then later evolve your learning from it and implement it across. So initially you might have to spend 2 3 weeks, I would say even 4 weeks, if starting incremental adoption. Start with critical services, permanent gains replicate to every service. Once you implement it, it's easily replicable to any other service. And the break even time is around 6 to 8 weeks, because given like everybody is spending 15 to 20 hours, that time would drastically reduce to 4 to 5 hours, right? Around 80% reduction. So in 6 to 8 weeks, or maybe 10 weeks, you get your ROI, or time spent in resource allocation and engineer time spent in designing this whole infrastructure. So the key insight here is that the complexity you add at generation time eliminates exponentially more complexity at analysis time. So yeah, you are laying up the foundation, but later on when the incidents really happen, the complexity and the time spent on alert fatigue gets reduced drastically. So what are the key takeaways? So we'll now get into what have been the key takeaways for us when we have implemented it and others have adopted it. So first insight is that start with context enrichment. Again, as I said previously, begin small and think big. Don't implement the full three-layered architecture at once. Just start by enriching one critical service. So, minimum viable context, like essentially says what are your crucial tags. It could just be for cost tracking, that you are tracking a team's ID, for example, an owner tag, or like a service ID, and you know that this service really heavy load. So just start with the minimum viable context and also the minimum viable implementation. So for that we add dictionary, context dictionary to your logging setup, propagate context through service calls, include context in OTL spans, validate context appears in all signals, and expand to other services. So the first insight is that for one your week one goal is that pick one high traffic service and add basic context enrichment on that. You don't even have to add the analysis engine layer, the AI layer. The second insight is that it's very essential for us to make sure that our data is queryable, and we can draw insights from that. So make the data AI ready. Even without the full implementation, create structured APIs over all of your telemetry, the thing that we saw previously, based on request IDs, based on timestamp filtering. Create the APIs and integrate it with your dashboards wherever you view your telemetry, whether it be Grafana, Zipkin, Kibana, anything. So what are the benefits? So programmatic access, consistent interfaces, and AI friendly formats. And here I've provided some simple REST API patterns for the payment service which we used as an example. So the second insight is, and the quick win from here is that wrap existing observability tools with simple query APIs, as we spoke about, so that filtering and querying that data becomes easier. So inside three, I think this is a very well known fact in software engineering and also product development, is that we always iterate with feedback from either customers or from within. So from within, we say like operational feedback. So context is a living system, because context changes every day. The best schema emerges from real world incident patterns. So I would say like what we have basically leaned into is that we measure, refine, and expand. And what I mean by that is that we track which context field engineers actually use during incidents. If those fields are missing, we add those and remove the unused fields, so that we are not adding essentially like raw data which is not very actionable for even the AI models, and then expand that learning to different services incrementally. So the anti-pattern to avoid here is that don't try to design the perfect context schema upfront. Let on-call incidents and operational load guide you into designing the context schema. What's next? So let's see like what are we planning for the future, and then what are the enhancements that we want to do. So industry adoption and scalability. Here we talk about like the different phases in which like somebody wants to implement this, how would they implement it, and how have we thought about implementing it and also getting returns from our investment. So firstly, this solution scales from startups to enterprises. There is no one size fits all, but essentially here like anybody who uses this solution can morph it to their specific needs. So it's ideal for organizations with microservice architectures, cloud native deployments, distributed systems at scale, having a very cluttered, non-uniform observability stack, alert fatigue problems, and long mean time to detect and resolve essentially. So phase one, as I said, is like context enrichment, which is the key part. Then query layer, which is phase two, the basic APIs that you have, and then AI analysis, anomaly detection layer, basically, which and then scale for scale across services, and then do a full MCP implementation. So till here, I think a lot of folks like till phase four, a lot of folks, and we all have understanding of how things work, and this we can move fast even before getting into the complexity of the full MCP implementation. So what's the future of observability, and what we are seeing today is that observability is shifting massively from error prone, like fatigued reactive, to a more optimized proactive approach. So traditional observability, we wait for alerts to happen, hunt root for root causes, and do manual correlations. We do reactive firefighting and fatigued on-call engineers. Like on-call becomes usually a nightmare. However, in this new paradigm where we have AI-powered observability, which is full of context, enriched context, so we predict issues before impact. Even if we could solve like around 20% of the issues, and that is happening again and again, and we can predict them, it becomes very easy for us, for engineers to scale it. If the load is predicted to increase, like you can preactively scale it. You can also automate it if you have an MCP server, like it can scale on your behalf, but again, it can be manual or it can be automated. So AI suggested root causes. So if you get a boilerplate of the root cause, you at least get what is the hypothesis and deep dive into that for creating the public facing RCS usually. Automatic correlation, of course, proactive optimization you get, and the on-call engineers are empowered and they can focus on better things rather than solving the same problem repetitively. So from what from what we are seeing is that observability problem is fundamentally a data problem, and it should be solved at the data layer, not at the insights layer or the inference layer. So we should try to solve that at the data layer itself. Yeah, thank you. Hope you find this presentation insightful. Feel free to follow me on LinkedIn and Twitter, and these are my socials. I have put the sample code and references, and I've made it open source on my GitHub. So feel free to start it or use it and raise issues. If you want to reach out to me, here's my email. But yeah, it was really glad presenting this in front of you folks, and I hope you all have a great DevOps 2026. And I thank Conf42 and Mark for the opportunity to present, and I hope you guys liked it. So signing off. Thank you, everyone.